Electrochemical cell in organic synthesis. This process is also called preparative electrochemistry. Electrochemical cell contain power supply, electrodes, anode and cathode, reaction mixture, and supporting electrolyte. Terminologies used during organic electrosynthesis: power supply, electricity a source, current movement of electron, potential voltage difference between two electrodes provides energy to move electron, charge, current pass over time, electrode, conducting material that carries current into reaction solution, cathode reduction electrode, anode oxidation electrode, working electrode where the reaction of interest is happening, counter electrode opposite to working electrode, counter reaction on the counter electrode, cyclovoltammetry, an electrochemical analytical tool that is used to determine redox potential for electrochemical transformations. Overpotential. Additional potential required depend on the electrode material. Standard potential of a redox reaction under standard conditions. Supporting electrolyte, chemical species which has an ionic strength and conductivity is also called inert electrolyte or inactive electrolyte. Examples are tetrabutyl ammonium borate, lithium perchlorates. Some other indirectly related terminologies which are used in electrochemical synthesis: atom economy, maximizing the number of atoms of the raw material that are incorporated in the desired product. Faraday efficiency, the ratio of column consumed in forming the chemical product to the total number of columns passed through the cells. Oxidant economy, minimizing of the stoichiometric and non-renewable oxidant to affect oxidative chemical transformations. Resource economy, minimizing the overall footprint of the chemical transformation as to the complete life cycle analysis, including but not being limited to the use of naturally abundant or renewable feedstock, solvent, metal catalyst, energy, and redox reagent. Step economy, reducing the number of reaction steps for efficient chemical synthesis. Types of electrochemical cells. First is undivided cell. In an undivided electrochemical cell, the electrode and anodes are housed in the same chamber. This setup is easy to carry out as no glassware or reactor is needed. In addition, the distance between the two electrodes can be easily adjusted and the ionic species can move freely between the electrodes. Second is divided cell. In a divided electrochemical cell, the cathode and anode are kept in a different chamber separated by an ion-permeable membrane or salt bridge. When using divided cell, the resistance is typically high due to the separation of electrode, which may lead to the slow reactions. However, the divided cell allow the possibility of maintaining different chemical environment around the two electrodes, thereby bring out fine-tuned reactivity inaccessible via an undivided cell. Third type is Cosi divided cell. A cell design that combines characteristics of a divided and an undivided cell is realized in a Cosi divided cell. Success of the Cosi divided cell design is realized by two electrodes which have significantly different surface area and galvanostatic electrolysis under rather low current like 10 milliampere is preferred. At the two electrode, different scenarios are then realized. At the working electrode, the constant current of 10 ampere cause a low current density. At that electrode and the material with the lowest redox potential is transferred over nearly the entire course of the electrolysis, and only at the electrode of electrolysis undesired side reaction will occur. At the counter electrode also the 10 milliampere are following in the opposite direction, and because of the much smaller surface area of the wire electrode, the current density is considerably higher. The concentration of the starting material is relatively low and mass transfer to the electrode is insufficient. Therefore, a large portion of current is used to electrolyze the solvent, and thereby chemical shortcut is mostly prevented. Two types of modes of operations are used in electrochemical reactions. And electrochemical reactions can be executed at a constant cell current, known also galvanostatic, or a constant voltage or potentiostatic. In a constant current reaction, it is easy to calculate the total charge consumption. Disadvantage of the constant current reaction is that the voltage profile of the reaction is often overlooked. The potential that the reaction starts at and the way it changes throughout the course of the reaction are factors critical to the outcome of the reaction. As the result, active species deplete in the course of constant current reaction, the potential increases. If unattended, this can lead to the undesired redox process and become detrimental to the reaction. If the reaction is executed with a total amount of charge like 2 Faraday per mole, it is possible for the potential profile to stay within an acceptable range in the course of reaction. However, if a reaction is run constantly like 16 hours, it is especially important in this case to pay attention to the potential and make sure it stay within a acceptable range. In a constant voltage reaction, cyclovoltammetry studies are often required to set a potential value for the reaction. Constant voltage reactions are less prone to runaway side reaction. The potential range of a constant current reaction must be carefully monitored and controlled to avoid unattended redox process that may be detrimental to the reaction. Similarly, the current of a constant voltage reaction must remain at a sufficient level to achieve an acceptable rate of reaction. In both cases, cell resistance can be adjusted via electrolyte concentration, solvent, cell configuration, electrode surface area to achieve the control of voltage or current respectively. These both type of mode of operation, galvanostatic and potentiostatics, are possible in undivided and divided cell.